Here is the list of the items that I plan to go through today. I will start by telling you what a SNARK is, and then briefly tell you about this very popular proof of SNARK proving system called Plonk. Then I will discuss the scalability issue of Plonk and how Pianist, which is a distributed version of Plonk, solved that problem. And after that, I will give you some background on FRI, and then explain to you the construction of this distributed FRI-based polynomial commitment scheme, which is the focus of this master thesis. And then after that, we will look at a few different methods of running distributed FRI. And finally, I will show you the data from experiments comparing these methods of running distributed FRI together with some ideas for future work. So what is a SNARK? Essentially, a SNARK is a short proof that some computation was done correctly. So usually in a SNARK setting, you have a prover and a verifier, and the prover wants to make some claim, such as, I know some input x that hashes to 0. So in order to prove to the verifier of this fact, the prover computes this short string pi and send it to the verifier, which the verifier can then run this verification algorithm to check. And then if that algorithm outputs accept, then the verifier is reasonably sure the claim made by the prover is true. So why is this called a SNARK? Well, the S in SNARK stands for succinctness. So that means this short string pi must be easy and fast for the verifier to check. So specifically, this means that the proof size and verification time must be logarithmic in the size of the input statement. And then the N in SNARK stands for non-interactivity, which means this protocol is non-interactive, so it has a single round of communication. And finally, the ARG in SNARK stands for argument of knowledge. So this means any prover who is able to produce a convincing proof must actually know the input X. And finally, if furthermore that the verifier is not able to learn any information about this input X beyond the fact that it makes the claim true, then we say the SNARK is zero knowledge, and we call it a ZK SNARK. Okay, so now let me tell you just a little bit about this proving system called Plonk. So Plonk has three components. The first one is called Plonk arithmetization. So usually the most natural way of expressing the fact that some statement is true is by using these circuit constraints. So Plonk arithmetization is a systematic way of converting these circuit constraints into polynomial constraints. And these polynomial constraints usually look like some polynomials must vanish on a predetermined set. And then in order to prove that these polynomial constraints are satisfied, Plonk uses something called a polynomial IOP. So IOP stands for interactive oracle proof. And it is an interactive protocol run between a prover and verifier, where the prover sends oracles of polynomials to the verifier. And then the verifier sends back random challenges. So what do I mean by oracles of polynomials? Well, imagine that the prover is able to put this polynomial f inside a magical crystal ball and send it to the verifier. And then the verifier is allowed to ask this crystal ball questions such as, what is f evaluated at alpha? And then it is guaranteed to get back a correct answer from this crystal ball. So these abstract functionalities like oracles help us reason about interactive oracle proofs. But in real life applications, we do need a concrete way of instantiating these oracles. And that is done by using a polynomial commitment scheme. So KZG is the specific polynomial commitment scheme used in Plonk. And in general, a polynomial commitment scheme allows the prover to commit to some polynomial f. And what do I mean by committing to a polynomial f? Well, it's kind of like locking this polynomial inside a locked box and send it to the verifier. So just by looking at the commitment, the verifier shouldn't be able to figure out what was committed. And then after the prover has committed it, it shouldn't be able to change its mind about what was committed at a later point of the protocol. So then at some later point, the verifier is going to want to know, okay, what is f evaluated at alpha? And then the prover sends back this claimed evaluation together with an evaluation proof pi, which the verifier can check using a verification algorithm. And if this algorithm outputs accept, then the verifier can be reasonably sure that the evaluation was provided honestly. So that was a very brief overview of the Plonk proving system. So Plonk is designed to run on a single machine. And for that kind of snark, we call it a monolithic snark. However, monolithic snark don't scale. So an experiment from Pianist shows that even if you have a machine with 200 gigabytes of memory, the largest circuit that you can use Plonk to prove on that machine has only up to 2 to the 25 gates. So Pianist is a solution to that problem. Essentially, Pianist is a distributed version of Plonk. And in the Pianist setting, you have one master node that is coordinating multiple worker nodes. So Pianist divides the work of computing this snark proof of a very large circuit evenly among its worker nodes. And in fact, it is able to achieve linear scalability for provers. So that means you can double the number of machines, and then the runtime and memory cost of each worker node will decrease by a factor of 2. Also, Pianist has very little communication among these worker nodes. It also inherits the constant proof size from Plonk. So here is an overview of the Pianist proving system. And as you can see, it looks very similar to Plonk, except that for every component of Plonk, you have a corresponding bivariate version of it. So for example, in Pianist arithmetization, it similarly converts these circuit constraints into polynomial constraints. It's just that now those polynomial constraints are expressed using bivariate polynomials. And then Pianist also has the bivariate polynomial IOP, where the prover sends to the verifier oracles of bivariate polynomials. Also in Pianist, they designed a distributed version of the KZG polynomial commitment scheme, which allows the prover to commit to a bivariate polynomial f, and then allows the verifier to later query this polynomial f at a pair of points. So now let's take a closer look at the polynomial commitment scheme that was used in Plonk and Pianist. So one of the most amazing aspects of KZG is that it produces proofs of constant size. This means no matter how large the polynomial, no matter how large the committed polynomial is, the evaluation proof output by KZG always have the same size. However, KZG does require a trusted setup. So that means you need some trusted third party to generate some parameters for you to be used in the proving system. And if those third parties cannot actually be trusted, then the integrity of the entire proving system is compromised. Also, KZG is not post-quantum secure because it relies on the fact that one cannot efficiently compute discrete logarithms. There's this other type of polynomial commitment scheme called a FRI-based polynomial commitment scheme. So compared to KZG, it does have a larger proof size, which is polylogarithmic in the size of input. However, it doesn't require any trusted setup. It is also plausibly post-quantum secure. So what is this FRI-based polynomial commitment scheme? Before I can tell you what it is, let me first introduce FRI. So FRI is a low-degree test. It is an interactive protocol run between a prover and verifier to prove that some committed function is close to low-degree polynomials. So at the beginning of FRI, we assume that the verifier already has the commitment of some function f, and then the claim made by the prover is that f is close to polynomials of low degree. So then they run this FRI protocol, and in the end, if the verification algorithm outputs accept, then the verifier knows that the committed function was indeed a low-degree polynomial. So using FRI, one can build a polynomial commitment scheme. This is how it works. So after the prover has committed the polynomial f, now the verifier wants to query f at some point alpha. And the prover claims that f of alpha equals v. In order to prove to the verifier that this evaluation is correct, they make use of this very convenient fact, which says that a polynomial f is, which says that a function f is a polynomial of degree bounded by n, and that f evaluated at alpha equals v, that is equivalent to this quotient being a polynomial of degree bounded by n minus 1. So if you look at the condition on the left-hand side, that is what the prover wants to prove to the verifier. And it does so by using what's on the right-hand side. So to use that, they run the FRI low degree test on this quotient, and that is sufficient to prove the evaluation was provided honestly. So now I can finally tell you what this thesis is about. So the question that I want to ask is it possible to construct a bivariate version of the FRI-based polynomial commitment scheme so that it can be used together with Pianist's bivariate arithmetization and its bivariate polynomial IOP to obtain a SNARK that is transparent and post-quantum secure? And further, is it possible to make it efficient and horizontally scalable? So the answer to the first question is yes. And now let me tell you how to construct such a polynomial commitment scheme. Actually, before I do that, I need to explain this abstract functionality that is used in the construction. So this is called distributed FRI. If you look at it, it looks very similar to FRI, except that now the verifier has the commitment of a bunch of functions. And the claim made by the prover becomes all these FIs are close to polynomials of low degree. So then distributed FRI is this algorithm run between them. And then in the end, if the verification algorithm outputs accept, the verifier should be convinced that all FIs are close to low degree polynomials. And then using distributed FRI, here's the construction of the polynomial commitment scheme. Actually, before I explain the polynomial commitment scheme, I would like to draw your attention to the specific type of bivariate polynomials used in Pianist. So they all come in this very specific form. So it's not just any bivariate polynomials. So they are all sum of m terms, where m is the number of machines. And then for each term, it's a product of a univariate polynomial in x and a univariate polynomial in y. So this fi is the local polynomial held by the Irish worker node. And that might contain private witness information held by that worker. And then this Ri of y is a public polynomial. In fact, it is the ith Lagrange polynomial defined on the absolutes of unity. So to commit to such a polynomial, the prover simply computes the Merkle commitments of each fi and send them all to their verifier. And then at some later point, the verifier is going to want to query f at a pair of points alpha beta. To do that, the verifier will send over the first coordinate alpha to the prover. And then the prover is going to reply back with a list of claimed evaluations. So the prover claims that each fi evaluated at alpha equals zi. And the way the prover proves to the verifier that these are provided honestly is by running distributed FRI on this list of quotients. So if you remember from the univariate FRI-based polynomial commitment scheme that we talked about before, once you have proven that this quotient is close to a low degree polynomial, then you have proven that Fi is close to a low degree polynomial, and then Fi evaluated at alpha equals En. So this is what they do. And the verifier is gonna check this distributed FRI proof. And if it checks out, now the verifier is able to compute the full evaluation by computing this linear combination on its own. So here's the cost of the polynomial commitment scheme. For the prover, apart from proving distributed FRI, it also needs to spend big O of T log T time on committing the bivariate polynomial. So this is coming from having to compute the evaluation vectors in the commitment phase using FRT. And then for the verifier, apart from verifying distributed FRI proof, it also needs to spend time quadratic in a number of machines to compute this final evaluation. So at this point, I have not explained to you how exactly one would run this distributed FRI, and this is what I will do now. So just to recap, the goal of distributed FRI is that so each prover node Pi has its own local polynomial Fi, and then together they want to collectively prove to the verifier that each Fi is close to a low degree polynomial. And here is a list of performance metrics that we're interested in when designing distributed FRI. So ideally, we want small prover time and memory cost. We want as little communication between the prover nodes as possible. Also, we would like the prover cost to be linearly scalable. So that means if you double the number of machines, the prover cost decreases by a factor of 2. And finally, we don't want this to be too expensive for the verifiers, so it should have short verification time and a small proof size. So before I can explain to you how to run distributed FRI, I need to tell you more about this FRI low degree test. So at the heart of the FRI low degree test is this folding operation, which takes as input a polynomial f and use a verified provided random value r and fold it into a new polynomial that has half the degree. Okay, so how is this done exactly? Suppose you have a polynomial f of x, then you can group together all of its even degree terms and group together all of its odd degree terms. And then for those even degree terms, you can write it like this as f even evaluated by x squared. And then for the odd degree terms, you can factor out a copy of x. So the rest will be a sum of even degree terms. So you can similarly write it as f odd evaluated by x squared. And if you look at this equation, f even and f odd now should have degree that is at most a half of degree of f. So the new polynomial that you obtained is f even plus this verified provided random challenge times f odd. And similarly, this f new will also have degree that is 1/2 of degree of f. So the intuition for the FRI low degree test is that because the prover wants to prove to the verifier that this f0 is a polynomial of low degree. However, it is very expensive to just send the entire polynomial to the verifier and ask it to check. So instead, what the prover does is that it repeatedly applies this folding operation to get a smaller and smaller polynomial until it gets a constant polynomial. And now it's trivial for the verifier to check that this polynomial has low degree. So this is exactly what it does. So at the very beginning, the prover is going to commit this polynomial and send it to the verifier. And then the verifier is going to sample a random challenge R1, send it to the prover, Now the prover is going to use this random challenge to fold F0 to a smaller polynomial F1, and also commit it and send it to the verifier. And then, as you can probably expect, the verifier now samples a second challenge R2 and send it to the prover, and the prover folds F1 using R2 to get an even smaller polynomial F2. So they just repeat this process a couple of times until the prover has obtained a constant polynomial C. And then in this very last round, it no longer needs to commit to the polynomial, it just sends this constant value C to the verifier. Okay, so what I have just described is the folding phase of FRI, and it has a second phase called query phase. Essentially, during this query phase, the verifier is going to quiz the prover at several locations. So it needs to make sure that the prover during the folding phase has correctly folded those polynomials. So as you can imagine, a malicious prover could just commit an arbitrary small degree polynomial instead of honestly folding it from F0. So in order to check that, the verifier is going to sample a random set of query positions, Q, and send it to the prover. And then the prover needs to open every one of these FIs at some fixed position, determined by what's in the query set. So if you look at this expression carefully, so I have highlighted the positions that the prover needs to open at every layer. So for example, the prover needs to open F0 at G and negative G, where G is a query position coming from the query set Q. And then at the first layer, it needs to open F1 at G squared and negative G squared. And then this pattern just continues. So what does the verifier needs to do to check this FRI proof? Well, first of all, it needs to check that all the Merkle opening proofs are valid against the commitments previously made in the folding phase. And then it also needs to do this round consistency check. So what this is doing is exactly checking that each step of folding was performed correctly. So if you look at this expression, it is saying that, for example, at the first layer, the verifier needs to check that F1 evaluated at G squared is this very specific linear combination of F0 opened at G and F0 opened at negative G. And this check is repeated across every two adjacent layers. So that is the FRI low degree test. And so sometimes one would like to prove a bunch of functions are close to low degree polynomials. And the naive way of doing that is to just run FRI on every one of them. However, that is very expensive for the verifier. So it turns out that there's this way of proving that a bunch of functions are close to low degree polynomials by running a single round of FRI. And this is called batch FRI. So the way it works is as follows. So the verifier is going to sample a random challenge data called the batch FRI challenge and send it to the prover. And then the prover is going to compute this linear combination using theta and obtain a new polynomial f. And then they just need to run FRI once on this new polynomial f. In addition to that, the prover also needs to open each FI at all the query positions requested by the verifier. So what the verifier needs to check in this case is that this FRI proof on F is valid. So that proves that F is close to low degree polynomials. It also needs to make these linear combination checks, so the goal of these is to make sure that a prover at this step has computed the linear combination honestly. And the verifier just does that by doing some point checks at each one of the FRI query positions. So now this is the security theorem about batch FRI coming from that paper. So it says that if in the end, after running these verification algorithms, the verifier outputs accept, then with very high probability, all these FIs are close to low degree polynomials. Okay, so having explained the details of FRI, now I can finally explain to you how to run distributed FRI. So the most naive way of doing that is to just run several copies of FRI in parallel. So here you have m worker nodes, PIs, and then each one of them has a local polynomial FI. And now they just run their own instance of FRI. And that would produce m FRI proofs, which the verifier needs to check. So in terms of efficiency, one can expect that parallel FRI is perfectly scalable. It also has no communication whatsoever because each worker node only needs to focus on their own their own instance of FRI. However, as you will be able to see, parallel FRI is the most expensive for verifiers among all these distributed FRI methods. Now, this second method comes from researchers from Neo Research. They did not actually give their method a name, but for convenience, I will call it distributed batch FRI. So this is essentially several provers are running the batch FRI protocol together. So you have the verifier sending over the batch FRI challenge. And now each worker node is going to multiply its local polynomial by this appropriate power of theta, and then send them to the master node, which the master node will then sum up to get f. And then they run, the master node runs batch FRI on f. So overall, this will produce a batch FRI proof. So for efficiency, distributed batch FRI has a smaller proof size compared to parallel FRI because the verifier only needs to check a single batch FRI proof. However, it does have a very large communication cost and a large memory cost. And the communication cost is linear in the overall instance size instead of being linear in the size of the subcircuit. What is worse is that this is not relieved by increasing the number of machines. The third method is called fold and batch. This is the distributed FRI method that was explored in this master thesis. So essentially, it is a combination of local FRI folding at each worker node and the distributed batch FRI. So at the beginning, you have each worker node just fold their local polynomial to a smaller one. So this looks like parallel FRI. It's like a parallel FRI that's not finished. And then the rest is exactly the same as distributed batch FRI. So the verifier sends over this batch FRI challenge theta, and the worker nodes multiplies by theta, by some power of theta, and send these evaluation vectors to the master node, and then the master node then sums up and do batch FRI. So this, if you look at this second phase, it looks the same as distributed batch FRI. Then in this case, what does the verifier need to check in order to ensure everything was computed correctly? So the verifier needs to check that the partial folding proofs coming from each one of these worker nodes are valid. And then finally, in the second stage of the protocol, it generates a batch FRI proof, which the verifier also needs to check. then if we compare the efficiency of fold and batch with distributed batch FRI, then fold and batch has a larger proof size. And this is because the proofs coming from the first phase of the protocol where the worker do these local FRI folding are not batched. So basically, the verifier would need to check m copies of them. And however, if you look at the communication cost and memory cost, those are smaller compared to distributed batch FRI. This is because when those worker nodes are sending the evaluation vectors to the master node, they have already been folded to a smaller size. And finally, fold and batch is adjustable, so you can adjust how much folding are done locally at each worker node versus how much is done at the master prover. And as a result, it can have an efficiency profile that is either closer to parallel FRI or distributed batch FRI. So now let me show you the data coming from the experiments comparing these different distributed FRI methods. So the implementation is based on an existing SNARK implementation called Winterfell. And all the experiments were run on the server with 377 gigabytes of RAM. However, since I did not implement the network communication part of the protocol, the measured runtimes do not include time spent on communication, which is why I have included a separate graph showing the overall communication for all these methods. And finally, those Merkle trees used in FRI were instantiated with Leuven. So here is the performance for worker nodes. So these are the data from a single worker node. And as you can see, the worker nodes indeed have linear scalability. If you look at their runtimes and memory cost, if you double the number of machines, which is being shown on the x-axis, then the proof indeed goes down by a factor of 2. And then this is the overall performance for provers. So these are measurements coming from the master node. The master node, apart from having to coordinate all the worker nodes, also does the work of a single worker node. So this is indeed the cost for provers overall. And as you can see, it only has limited scalability. So at the beginning, you could get some benefits by increasing the number of machines. But beyond a certain point, those benefits start to diminish. And here is the overall communication cost for the two methods that actually have communication. For distributed batch FRI, it has a constant amount of around 4.3 gigabytes of communication. And that is coming from all these uncompressed evaluation vectors sent from the worker nodes to the master node. And then for fold and batch, it has a constant amount of about 1 gigabyte of communication for exactly the same reason. Except that now those evaluation vectors have been folded to a smaller size when they're sent to the master node. And this is why you're seeing like a factor of 4 reduction in communication costs. And finally, we have the verification cost. As you can see, parallel FRI is the most expensive for verifiers, followed by fold and batch, and then the cheapest for verifier is distributed batch FRI. However, in all three methods, if you increase the number of machines, the cost for the verifier goes up. So to summarize what we have seen in the experimental data, I have drawn this prover-verifier trade-off graph where the x-axis tracks the verifier's cost and the y-axis tracks prover's cost and prover scalability. And first of all, I want to put distributed KZG out there. So distributed KZG, if you remember, is the polynomial commitment scheme used in Pianist. And to be honest, it is not entirely fair for me to compare it with distributed FRI methods because it is by itself a polynomial commitment scheme, where these distributed FRI methods are subcomponents of a polynomial commitment scheme. However, it is still sitting at the best spot there is on this graph because it has perfect prover scalability. It also has constant verification time and proof size. And then you have parallel FRI, which is also linearly scalable for provers, but it is very expensive for the verifiers. And then for distributed batch FRI, it is less scalable compared to parallel FRI. However, it is cheaper for verifiers. And then in between these two methods, you have float and batch. So now I would like to briefly summarize the scalability bottlenecks that we have seen in the experimental data. So the first one is that the master node runtime and memory cost are not linearly scalable. So this is true for distributed batch FRI and float and batch. And the reason for that, as I have mentioned, is because the master node has to receive all these uncompressed evaluation vectors from the worker nodes. The second bottleneck is that the verifier cost goes up as you increase the number of machines. So this is true for all three methods. And if you look at the batch FRI protocol, this is due to the lack of homomorphism in Merkle tree commitments. So why do I say that? If you look at what's in a batch FRI proof, you have commitments, you have the Merkle tree commitments, and you have the Merkle tree opening proofs. Those commitments are pretty small, so it's mostly the opening proofs. If you count the number of opening proofs per FRI query needed in batch FRI proof, it is m plus log t. So that tells you why, as you increase the number of machines m, you get larger batch FRI proofs. That is all I have for this presentation. Thanks for your attention.